In this video, we're going to view the concept of formal charges. So sometimes when you draw a Lewis structure, you'll have several structures that seem that they could work. They follow octet rules, they have expanded or not expanded or less than expanded. So the incomplete, and you have to choose between two structures that look like they could both work. And in those cases there, you need to figure out which one is a preferred structure. So there is a system in place called the formal charge system or formal charge equation. There's a great video here that you could watch about it right here. So I do recommend you watch that for other examples. But basically, when you look at a formal charge, it's not really a real charge, but it's a way to compare the charge on the neutral atom in the molecule compared to what its charge would be in that molecule if you kind of spread the electrons all the way around, the valence electrons all the way around. And so the way to typically calculate the formal charge is you do the number of valence electrons on the particular atom you're interested in, minus the number of non-bonding electrons that you have present, and then minus the number of electrons in bonds divided by 2. In other words, minus the number of lines connected to it. And in general, once you've calculated the formal charges for all the atoms in a molecule, what you do is you compare formal charges on both structures you drew, and you would choose the best one based on the following rules. Usually, if all the formal charges are 0, that's what's preferred. For a neutral molecule. If you have a polyatomic ion, the formal charges need to add up to the overall charge of the molecule, of the polyatomic ion. But you want essentially them to be as close to 0 as possible. So if you can't get non-zero charges, then the smallest non-zero charges would be preferred. And there's other preferences, but for the most part in grade 12, we're going to be focusing on rules 1 and 2. And it really, really sounds complicated at first. But we're going to do a few examples, and I think once we do a few examples, it'll be a little bit less complex. So here we have the So2 molecule. And when you draw the So2 molecule, you'll get sort of two different possible structures that could work. You'll get this first structure, structure number 1, and then structure number 2. They both work because sulfur can have an expanded octet, so it's okay for it to have double bonds, 2 double bonds instead of just 1. But this one would work just fine as well because it has a satisfied octet. So what's the best situation in this case? The one with the satisfied octet, and the one with the expanded octet. So formal charges can help us to figure out which is the best structure. Let's calculate the formal charges for oxygen over here. Oxygen, just the regular oxygen, would have 6 valence electrons normally, minus, now how many non-bonded electrons are there? There's 4, minus the number of lines connected to it, 2. And so that gives us a 0 there. That gives us 0 formal charge. Let's go and calculate the formal charge of the oxygen over here. So I'm going to put 0 up here, formal charge. And we're going to do the same idea here. So 6 valence electrons normally. And right now in the molecule, there's 6 dots around it, so minus 6. And there's 1 line connected to it. So we have minus 1. And that gives us an overall formal charge of minus 1. So this oxygen over here has a formal charge of minus 1. And now we're going to do the formal charge of the sulfur in the middle here. And so generally sulfur has 6 valence electrons minus the 2 dots connected to it, minus 3 lines connected to it. And so that's 6 minus 2 minus 3, that's plus 1. So we have a plus 1 formal charge on the sulfur. Overall, the formal charges are add up to 0, which is good because the overall molecule is 0. But let's see if we can get a molecule. Let's see if we are at a structure over here, we'll have formal charges that are better. Can we have all zeros all around? Let's take a look. So if we go over here and we take a look at the formal charge of the oxygen here, oxygen normally has 6 valence electrons, minus the 4 electrons connected to it, minus 2 dots, that's 0. And this looks like the same sort of setup, right? 6 minus 4 dots minus 2 lines, that's 0. So both these oxygens have a 0 formal charge. And if we look over here at the sulfur, let's take a look at that one. This sulfur here, you'll notice has, normally 6 valence electrons minus 2 dots connected to it minus 4 lines, that's 0. So all the formal charges here are 0. That's our preference. So that means this is our preferred structure. Chances are this may contribute in some way to the overall structure, but we don't really know. It's not the preferred structure. Likely it is this structure over here that's preferred. So it's better to have the expanded octet where the formal charges are all at 0. So this is your better structure here. So if you can have situations where you have a choice between the just stable octet and the expanded octet, you need to choose between the two structures that would best fit the situation. And to do that, you would use your formal charges. So in this case, the best structure is this one here with the minimal formal charges, 0, 0 all around, nice and spread evenly. Now these, just to clarify, these are not necessarily resonance structures in the traditional sense, because if you look at resonance structures, their formal charges would be equivalent. So the example we saw in the previous video was this here, where we had this is resonance. And so the formal charges will be equivalent in these two structures here, whereas in these two structures up here, they're not equivalent. So they're not really considered significant resonance structure contributors. They really do have to be equivalent. So if we did our formal charges for something like this molecule here, just to test it out, let's just put our dots there. For this, for example, you'll have 6 minus 4 minus 2, that's 0. For this one here, you'd have 6 minus 3, 1, 2, 3, minus 2, that's plus 1. And for this over here, you would have 6 minus 6 minus 1, that's negative 1. So you'd have negative 1 and plus 1 here. Whereas here, this one would be 0, this would be your negative 1, and this would be your plus 1. So the formal charges are essentially the same relative to each other, which is why these are actually considered resonance structures. And one more thing to mention as well is some students might say, well, aren't these formal charges pretty high? Negative 1 and positive 1. So could we make more double bonds on the oxygen and make our formal charges 0? So could we do this, for example? Could we try this out like this and maybe have better formal charges, because we want to try to reduce formal charges as much as we can and bring them close to 0. So you can try that, and if you did this, you would get 6 minus 4 minus 2, that's 0. Here you'd have 6 minus 4 minus 2, that's 0. And then here you'd have 6 minus 2 minus 4 again, and that's 0. And so you might say, well, these are all 0, 0, 0. So this is the better structure. However, what a lot of you are probably saying right now, no, this is wrong. You can't do that. Look, oxygen is in period 2. It can't have an expanded octet, so you cannot choose this one. This is not a situation where you're going to try to use formal charges to choose which is the best structure. And it's the same thing with because you just can't have an expanded octet. So this is not even a choice. And with resonance structures, you're not trying to calculate formal charges to figure out which one's the best structure, because they're all equivalent structures in terms of their formal charges. They all contribute significantly. So don't get that confused with when we're using formal charges. We're using formal charges where there's a difference. Notice these are different. There's double bond, single bond. Here there's 2 double bonds. Whereas here we have double, single, single, double. It's the same thing, equivalent overall. So you're really going to use formal charges when they don't look equivalent, and you have the possibility of choosing between the two, and you want to choose the one that has the minimal formal charges of 0. And if you can't have 0, then you want to make sure that you choose the ones that have the minimal charges, the smallest non-zero charges. So in the next few videos, we'll be doing some examples of molecules that may have more than one possible acceptable structure. And to figure out which one is the acceptable structure, you're going to have to use the formal charge technique. So I'd recommend before watching that video, you try these examples out over here, and then you can check back in to see if you're on the right track.